What's up, guys? This is Jahangir from Medporium, and today we're going to be talking about resonance structures. So the easiest way to explain resonance structures is that we can have more than one Lewis structure or Lewis formula. So resonance structures really help us illustrate delocalized pairs of electrons. So these are pretty much shared electrons. And with resonance structures, like we said, we're going to have more than one Lewis formula. This really illustrates how electrons can be shared between different structures, how electrons can pretty much move around. To illustrate this, let's write the resonance structures for ozone, which is going to be O3. So just as extra practice, we have an oxygen, oxygen over here. So first thing we could do is just assume that they all have a bond, because to actually be bonded together, they have to have at least a pair of electrons that are being shared. So we can safely assume that. Now we just go around and see how we could fill that octet rule as well as the amount of valence electrons. So we'll start with this oxygen to the left, and we could say that this is a double bond because we're going to have 6 valence electrons and fill that octet rule. And usually you'll see if oxygen is not bonded to hydrogen, it's usually going to have a double bond, but we still have to check. So if we have a double bond over here, we have 1, 2, 3, 4. We have 4 valence electrons. We still need 4 more to fill the octet rule, and we have 2 valence electrons over here. So we still haven't filled that valence electron part. So if we put a double lone pair over here, then we fill both rules. Now over here with this oxygen, so far we have 6 electrons. So we need 2 more to fulfill that octet rule, and we can just do it like that. So one thing that you have to understand with these Lewis structures is that the octet rule is the most important rule that we need to fill. Now these are for elements that are in row 1 and row 2, because when we go beyond that, they actually don't have to follow the octet rule, which we'll talk about later. But oxygen needs to follow the octet rule. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we have 1, 2, 3, 4, 5 valence electrons. So we're going to have a positive 1 formal charge for this oxygen over here. Now, this oxygen over here, since we can't put a double bond, if we do, we're going to break this octet rule for the oxygen on the top. Then we're going to put all of our lone pairs, and this is going to get us a -1 formal charge. Now, this is just one of our resonance structures, and this is how you want to draw your resonance structures. Having brackets, and let me just erase this O3 over here so I can illustrate the other resonance structure. Now, if we had a overall formal charge that was -1 or +1, then we'd add it over here. But since that minus formal charge from this oxygen over here cancels out that +1 charge of the oxygen over here, they balance out, so we're going to get a overall formal charge of 0 for that ozone. Now, next, we want to use these double arrows to show that we have another resonance structure. And here's the thing about understanding what the next resonance structure is going to look like. Now, a simplified and maybe even oversimplified way of thinking about it is just moving the bond around. If we have a double bond over here, we're just moving the double bond. So what would happen is we'd have this oxygen over here, filling that. This oxygen will stay the same with 2 valence electrons, and then over here we'll have that double bond for that oxygen. So we're pretty much moving the bond. This clearly shows a delocalized pair of electrons in which 2 of these pair of electrons can move around. Now, the easiest way of understanding resonance structures, and this is how I understand them, is, like I said, just moving the bond. If there's most likely there's going to be a double bond with these resonance structures, because, for example, if we're looking at methane over here, we have CH4. There's no double bond, so the electrons can't really move around. But as you can see with this oxygen over here, we have this double bond, so meaning we have 2 electrons that can actually move around. So if that's still not making sense, don't worry, because we're going to go through another practice problem. So for our next question, we want to ask if there are any resonance structures in sulfite. So I want you guys to pause this video and see if you can write all the Lewis formulas and see if there's any resonance structures. And if there are, try to write as many of them as you can. So we first need to obviously start by writing our Lewis formula for sulfite. So we're going to have a sulfur in the middle, and we'll say we have a bond between this oxygen, oxygen, oxygen. So we want to assume that there is going to be a bond, because if there's no bond, then these molecules can't be attached to each other. And we really have to pay attention to this 2 minus over here. So that's indicating that we're going to have a negative charge. So the only way we're going to have a negative charge is if some of our atoms have a negative formal charge. So now if we're going to go looking through our Lewis formula, now what we can do automatically is just put out all of our lone pairs over here for that oxygen and over here for this oxygen as well. Now the problem is, the reason why this isn't our Lewis structure is because all of these oxygens are going to have a -1 charge, -1, -1. So that means that we're going to have an overall charge of -3, which we can't have. We're trying to find a charge of 2 minus. So that's why we might have to put a double bond in one of these oxygens. So then we can counterbalance one of those charges. We can have one of those oxygens have a neutral formal charge, and that's why there's going to be a double bond between one of the oxygens. Now, with resonance structures, we're just going to be moving around the bonds, because we're assuming that there's a delocalization in a pair of those electrons, where we're just saying that those electrons can move around. So an easy way to understand these resonance structures is each of these oxygen atoms are cars, and these electrons are drivers. And these drivers can move around through each of these oxygens. So just to illustrate that, we need to write our formal charge over here. So oxygen is going to be -1. This is also going to be -1. So we're going to fill in our brackets over here. This is going to be an overall -2 minus charge, so we can show that. And all we have to do is just move around the bond over here. So same exact thing, but let's just do, for example, this oxygen over here. It really doesn't matter which order you put those bonds, as long as, or those double electrons, which part of the sulfur and the oxygen is connected, as long as you show every single configuration that could be possible. So we have this over here, and our final resonance structure, and let me put a 2 minus over there. So we can say that we'll put that pair of electrons on the right oxygen. So put those lone pairs over here. And yeah, it is kind of tedious to go through each of these resonance structures, but this might be something that you'd have to write down in some of your multiple choice questions or even free responses. And we'll have a 2 minus over here. So when I was talking about the analogy of cars and drivers, see, as you can see, our oxygens are the cars, and our cars pretty much stay the same. We could say, like, this is a Porsche, this is a Ferrari, and this is a Lamborghini. Now our electrons are our drivers, and maybe one day our drivers want to drive a Porsche, but then the next day they want to drive a Ferrari, and then the next day they want to drive a Lamborghini. And this is what results in stabilization of this molecule of sulfite, is when these electrons or these drivers can move around with these different cars. And overall, we can demonstrate this entire resonance structure as having a sulfur over here, then the bond of the oxygen, and we can use these sort of little dots to indicate that the electrons can move towards this side. We can have the same thing for this oxygen over here, and the same thing for this oxygen over here. So this is really just illustrating that these pairs of electrons can move around different cars. These drivers can move around different cars. And these electrons in double bond can move back to the oxygen, which is what creates this resonance structure. And what can happen over here is our curved arrow will move those two electrons, just indicating the movement of the electrons move back to that oxygen, while these electrons can move to this sulfur to make a double bond. So curved arrows are a great way to demonstrate how our electrons are pretty much moving. Now, there are also some qualifications that can allow some of these resonance structures to be a major resonance structure and a minor resonance structure. So one of them is having the most bonds. So one qualification of being a major contributor is having the most bonds. And this is seen with formaldehyde. So if we were trying to lose the structure of formaldehyde, we'd have C, then an H over here, hydrogen, and a double bond of oxygen. And we might say something like that. So this would be major. And This has the most bonds compared to our other resonance structure, and we're going to have something like this, and oxygen is going to have a minus formal charge. So we could have a resonance structure of this for formaldehyde as well. And just to write our arrows over here, we'd have these two electrons move up, which would result in this positive formal charge for our carbon and this negative charge for our oxygen. So this would be minor because the major contributor is going to have the most bonds. If we have most bonds, then we're going to be more stable. Now, another qualification we could have for a major contributor is having neutral formal charges in our atoms. So what's an example of this? An example of this is methyl nitrate. So if we write the Lewis structure of that, it'd be CH3, and it would be bonded to an oxygen over here and a nitrogen, and we'd have a double bond of that oxygen over here. So this is our Lewis structure of methyl nitrate. And as you can see, we're filling all the octet rules. We filled all the valence electrons, so we don't have any formal charges. Now, another resonance structure, and we're moving around the bond. Another example of a resonance structure that we might see is we still have our CH3, and we can say we have oxygen over here, but the double bond is between this oxygen over here and this nitrogen, and we'd have a single bond over here. So what would happen is this oxygen would have an extra valence electron, which would make it negative on the negative side, while this oxygen over here, we could just put a lone pair to fill our octet rules. But if we're looking at formal charge, we have a positive formal charge, and these still cancel out because we have a overall negative formal charge. We don't have any charge in our entire molecule, and this is still a resonance structure, but the reason why this one is minor and this one is major is because we have neutral formal charges in all of our atoms in this resonance structure over here compared to this one. Now here's another qualification to be a major contributor and another one to be a minor. So if we have a negative charge, so we'll say we have a negative charge on the most, and I'll just put E negative just to represent our electronegativity, so I'll put E neg. If we have a negative charge on the most electronegative atom, then this is going to be our major contributor. Now let me change my color over here, and if we have a positive charge on the least electronegative, then this is going to result in our major contributor. So the opposite of that would be our minor contributor, because if we know our major, then we obviously know our minor. So an example of this would be cyanide. So what is the Lewis structure of cyanide? Well, we're going to have a nitrogen, and we're going to have a triple bond with a carbon, and we're going to have this oxygen over here. And here is one of our resonance structures for cyanide. And over here, this oxygen is going to be negative, so our overall charge is going to be negative. So cyanide is going to have a negative charge. So our other resonance structure, if we pretty much move this triple bond, this would result in a nitrogen over here, and we'd have that one of the two pairs of electrons would be moved to the other side, so they'd travel to the other side. So we have this carbon over here, this oxygen, and all of it is filled until this nitrogen, where with this nitrogen, we have to have two lone pairs, because if we leave one lone pair, then we're going to have a positive charge, which we want an overall negative charge. So this nitrogen is going to end up having a negative formal charge, and this is going to be negative. Now, if we're following our rule of negative charge on the most electronegative is major, positive charge on the least electronegative is major, we're looking at negatives first. So we can forget about this rule of the positive charge because we only have negative charges. Now, if we look at each of our resonance structures, we see that oxygen has a negative charge in this resonance structure, while nitrogen has the negative charge. So I want you guys to pause this video and see if you can determine which one is a major and minor. And a hint is which is more electronegative. Basically, that's the question I'm asking. Which one is more electronegative, oxygen or nitrogen? Because if you can answer that question, then you automatically know which one is the major resonance structure. So the major resonance structure is this first resonance structure over here. The reason why is because oxygen is much more electronegative than nitrogen. Because if we look at our periodic table, going from left to right, we can see that oxygen is closer to fluorine because fluorine is the most electronegative. Anything closer to fluorine is going to be more electronegative than anything pretty much away from fluorine. So oxygen is closer to fluorine than nitrogen is closer to fluorine. So that's why oxygen is going to be the most electronegative, and we have a negative charge on that electronegative atom. That is why this first resonance structure is our major, and this one is going to be our minor. So hopefully that made sense with resonance structures, because I want you guys to remember that resonance structures are only when we're moving the electrons around. We're basically just moving the electrons around, allowing our drivers to test out any car that they want. So hopefully that made sense, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.